Welcome to KU Pathshala, a novel initiative of the University of Kerala to archive educative videos. CLIF is taking part in this venture wherein we are exposing the instruments being housed in the CLIF campus for the benefit of people who want to use the facility for their research purposes. The facility is managed by qualified technicians, highly trained, as well that governed or managed by faculty who are all experts in the field. The idea behind housing all the instruments under one roof is that not only that you will be able to use the instrument, but also get the feel of how exactly an instrument is functioning. For that matter, we are encouraging people to come to CLIF while their samples are analyzed so that they will be able to understand how the instrument is functioning to get the desired results. We have qualified faculty as well as outside experts who will be speaking during the video filming on the application value of each instrument being housed in this. The central instrumentation facility, which is being housed in the Karyutam campus, has got about 21 equipments, high-end equipments, being supported by different organizations in the country. I'm not going to the details of the functioning of the instrument as is going to be demonstrated in the videos. So I welcome you to view the videos, and straight away we see the videos about the functioning of the instruments which are housed in the CLIF campus. Thank you very much.
Welcome to KU Pathshala videos. Today we will be describing the photoluminescence spectrometer. Photoluminescence is the emission of light from materials due to the absorption of electromagnetic radiations. Photoluminescence can be classified into fluorescence and phosphorescence depending upon the origin of emission from which state. In 2019, CLIF installed a photoluminescence spectrometer called FLS1000 from Edinburgh Instruments. This instrument is one of the state-of-art facility for the analysis of luminescence materials. This instrument can measure photoluminescence from UV to mid-IR range, and it can also measure the decay lifetime from picoseconds to seconds with the additional facility of measuring the quantum efficiency of luminescent materials. This state-of-art facility can be useful for various researchers, especially researchers in the interdisciplinary areas like biophysics, biochemistry, chemistry, life science, and nanomaterials, etc.
Hi, welcome all to a session about sophisticated fluorescence spectrometer. Me, Vishnu P, Technical Assistant, Central Laboratory for Instrumentation and Facilitation, University of Kerala. The CLIF is a new and exciting initiative with number of analytical instruments under various schemes. The center represents one of the largest commitments for research in the history of university. As we all know, photoluminescence, simply PL, is an optical phenomena that semiconductors give light emissions by absorbing incident light whose energy is higher than the energy bandgap of the semiconductor. In the mechanism of PL, the excited electrons generated by the optical excitation will return to the ground state accompanied by emitting photons. PL measurements such as steady state and time resolved PL, PL decay, PL quantum efficiency are usually used to probe the fundamental radiative characteristics of semiconductors. We have a FLS1000 sophisticated fluorescence spectrometer of Edinburgh Instruments. Sets the standard in both steady state and time resolved photoluminescence spectroscopy for both fundamental research and routine laboratory applications. The system is a modular fluorescence and phosphorescence spectrometer for measuring spectra from the ultraviolet to the mid-infrared spectral range and lifetime spanning from picoseconds to seconds. We are using Fluoracle software, which is fast and advanced for the measurements. This instrument can be used to study photoluminescence property, that is fluorescence and phosphorescence of light emitting materials in liquids, films and solids. Further, it can be used for the absolute quantum yield measurements of organic, inorganic semiconductors. Lifetime analysis through time-gated electronics can be performed. As we are going to the principle, photoluminescence spectroscopy, often referred to as PL, is when light energy or photons stimulate the emission of a photon from any matter. It is a non-contact, non-destructive method of probing materials. In essence, light is directed onto a sample where it is absorbed and where a process called photoexcitation can occur. The photoexcitation causes the material to jump to a higher electronic state and will then release energy, that is photons. As it relaxes, the returns back to a lower energy level. The emission of light or luminescence through this process is photoluminescence. Hence, we get the spectrum of emission, and from that spectrum we can calculate the emission wavelength. The fluorescence lifetime is a measure of the time a fluorophore spends in the excited state before returning to the ground state by emitting a photon. The lifetimes of fluorophores can range from picoseconds to hundreds of nanoseconds. If a population of fluorophores is excited, the lifetime is the time it takes for the number of excited molecules to decay to 36.8% of the original population. The decay of the intensity as a function of time is given by IT equal to alpha e raised to minus t by tau, where IT is the intensity at time t, alpha is normalization term and tau is the lifetime. When a fluorophore absorbs a photon of light, an energetically excited state is formed. The fate of this species is varied depending upon the exact nature of the fluorophore and its surroundings, but the end result is deactivation, that is loss of energy, and return to the ground state. The absolute fluorescence quantum yield, eta, is by definition the ratio of number of photons emitted to the number of photons absorbed, that is eta equal to n emission by n absorption. Now we can move on to the instrumentation of this instrument. We have the power hub from which the entire power to the system is supplied from there, and we have a temperature controller which maintains minus 29.1 degrees Celsius every time. This is for cooling the source xenon lamp. Then we have sources. We have mainly three sources. One is xenon arc lamp, then the another one is the flash lamp, and the third one is the picosecond pulsed LEDs. Then we have the excitation monochromators. The excitation monochromators are kept here inside this instrument. This monochromator transmits a selectable narrow band of wavelengths of light from a wider range of wavelengths available at the input. Then we have this sample chamber. In this chamber, we are loading the samples. We have powder sample holder. This is the powder sample holder. Then liquid sample holder. It is inside this chamber. Then we have the integrating sphere for quantum yield measurements. This is the integrating sphere. After that, we have the detectors. We have PMT detector and in-gas detector. This is the PMT detector, that is the photomultiplier tube detector, which detects up to 750 nanometer. Then we have the in-gas detector, that is the indium gallium arsenic detector, which detects about 750 nanometer. We have powder samples as well as liquid sample for this analysis. For powder sample analysis, we are using the demountable cuvette. It's made up of quartz. For liquid samples, we have the cuvettes. Now we can load the powder sample in this cuvette. This is a demountable cuvette. Here there is a groove. We have to put the sample in this groove. Then close it with this top portion. Now we can load the sample to the powder sample holder and then close the lid. Now it is ready for analysis. Open Fluoracle software. Open signal rate window. Select the source as xenon lamp and detector as visible PMT. Give the excitation and emission wavelengths. Then adjust the bandwidth to become the emission around 2 lakhs. Then close the signal rate window. Open lambda. Give the start and stop range. Apply and start. Now the scan is running. We get a wavelength versus counts plot. From this, we can calculate the emission wavelength of the sample. For liquid sample, we have to use this cuvette for analysis. Take the cuvette, pipette the sample to the cuvette. You can load 3 to 5 ml of the sample into the cuvette. Close the cuvette. Now we can load the sample to the liquid sample holder. Now we can load the liquid sample in the liquid sample holder. Place it properly. just push that and then close the lid. Now it is ready for analysis. Open Fluoracle software, open signal light window, select the source as microsecond flash lamp and detector as visible PMT 900. Enter the excitation and emission wavelengths and adjust the bandwidth to become emission around 10,000 counts per second. Then close the signal light window. Open TOW manually. Select the time range and channels. Give the stop condition. Apply. Then new to start. Now we get the time versus counts decay plot. Now we can go for quantum field measurement. For that, we have removed the lenses in this position and we have inserted the integrating sphere. Open the integrating sphere. There is two positions. Initially, we have to keep reference in both positions. Keep the reference plugs in this position. And close the integrating sphere. Then close the lid. Now it's ready for reference measurement. Open Fluoracle software. Open signal light window. Select the source as xenon lamp and detector as visible PMT 900 plus integrating sphere. Give the excitation wavelength of the sample as excitation and emission wavelength. Then adjust the bandwidth to become emission around 10 lakhs so that the emission bandwidth should be 1/10 of the excitation bandwidth. Then close the signal light window. Open lambda, emission scan, tick the corrections, give the start and stop range, apply and start. Now the reference run is over. Save the file. For quantum field measurements, we are loading samples in this cuvette. Open the cuvette, take the sample and fill it in the cuvette. We have to cover the entire surface of the holder. Then close it. Now it is ready for the analysis. We can load this to the integrating sphere. Now the reference analysis is over. Open the integrating sphere. Take the reference in the position 1. Insert sample there. Then close the integrating sphere. And close the lid. Without changing any parameters from the reference run the sample. Emission scan, apply, start. Now the sample run is over. Save the file. Then for QI calculation, go to Analysis, Correction. Give the integrating sphere correction for both the sample as well as reference. And then combine the corrected graphs. Go to Analysis, QI Calculation. Then select the parameters as per the procedure we done. Fill the required fields in calculation page. And finally, we get the quantum yield value in percentage. The main applications of this instrument are band gap determination of semiconductors, fluorescence tags bar markers used to study the chemical equilibrium and kinetics, important for various organic and inorganic complexes, sensitivity to local electrical environment, polarity, track solvation dynamics, impurity level and defect detection, recombination mechanism, material quality, molecular structure and crystallinity, nanomaterial characterization. For interpretation of luminescence spectra, it is necessary to consider several analytical and crystallographic factors which influence the luminescence signal. With this, we can wind up this session. Thank you.